Let's talk about a word you've probably heard 1,000 times, encoding. It sounds pretty technical, maybe a little boring, but what if I told you that this one simple word connects the video you're watching right now, the way we make sense of the news, and even how AI like ChatGPT actually works? Well, stick around because we're going to connect some pretty wild dots.
So what is encoding? When you boil it all down, it's really just about transformation. You're taking information in one form and converting it into another. But as you're about to see, the reason why you're doing that and what you're transforming, well, that changes absolutely everything.
Okay, so take a look at these two images. On the left, you've got a diagram that looks like it's straight out of an engineering textbook for video compression. On the right, that's the blueprint for a groundbreaking AI model. They seem like they're from completely different planets, right? Well, they're not. And by the time we're done here, you'll see the one powerful idea that ties them both together.
All right, first up, the worlds we live in every single day. We're going to look at the engineer's encoder. This is the unsung hero that gets high-quality video to your screen without completely demolishing your data plan. So let me introduce you to H.264. This is one of the most popular standards for squishing video files down. Its whole job is to take these massive files and make them way, way smaller. We're talking about chopping the file size in half, sometimes even more, and most of the time you can't even tell the difference in quality. It's pretty amazing. And here's the core problem they were trying to solve. You see, a high-def video is just an avalanche of data. It's literally billions of tiny pixels changing color dozens of times every second. If you tried to send all of that raw data over the internet, it would be a disaster, slow, clunky, and super expensive. So the solution they came up with is just genius. Instead of sending the whole picture, frame after frame after frame, they thought, hey, what if we only send the changes? The encoder's job is to turn that raw video into a super efficient set of instructions about what moved and where it moved. And this is how they do it. The magic trick is called motion estimation. You see that little block of pixels in the current frame? The encoder literally goes hunting in the previous frame, the reference frame, to find a block that looks almost exactly the same.
So it really just breaks down into these three simple steps. First, find the matching block. Second, you record how it moved with a tiny piece of data called a motion vector. It's basically just a little arrow that says it went this far to the left and this far down. And third, you only send that tiny little arrow. You don't have to send all those pixels again. You just tell the video player where to find them in the last frame. That, my friends, is encoding for pure efficiency. Okay, so we've seen how engineers encode pixels to make things smaller and faster. Got it. But hold that thought for a second. What happens when the thing you're trying to encode isn't a block of pixels at all?
What if it's an idea? And just like that, we're jumping out of the world of engineering and into the world of culture and communication. Welcome to world number 2. Now we're looking at the theorist's encoder. This has nothing to do with file sizes. It's all about how raw events in the world get transformed into messages with a very specific meaning. This quote from the cultural theorist Stuart Hall just nails it. He argued that something that happens in the world, an event, it isn't automatically communication. It first has to be turned into a story. It needs a frame, a narrative, a point of view. In other words, it has to be encoded with meaning. Hall laid this out in a simple 4-staged model. It all starts with production. That's where the message gets encoded. But here's the kicker. It's not a one-way street. After the message is sent out, the audience has to actively decode it in stage 3. And how they decode it in stage 4 has real consequences. And this is where it gets really interesting. Hall said we have basically 3 ways to decode any message. You can take the dominant position, which means you accept the intended meaning completely. Or you can have a negotiated reading. You get the big picture, but maybe you tweak some parts to fit your own experience. Or you can be oppositional. You know exactly what they're trying to say, and you reject it completely. The meaning isn't fixed. It's a constant back and forth.
Okay, let's take a quick breath. We've seen encoding for technical efficiency with pixels. We've seen encoding for cultural meaning with ideas. Now, for our last and final stop, what happens when we build a machine whose entire job is to encode the very fabric of human language?
And that brings us to our third world, the AI's encoder. We're on the cutting edge now. Here, encoding isn't about making things smaller or crafting a narrative. It's about creating a rich, complex, mathematical representation of language that a computer can actually understand. Meet the transformer. This is the architecture that powers pretty much all the big AI models you hear about.
And yeah, it has an encoder on the left and a decoder on the right, kind of like the old models. But the way it does it, it threw the entire rulebook out the window. It all comes down to one thing, a mechanism called attention.
And the big idea here is something called self-attention. Think of it like this. When the model is looking at one word, say the word it, self-attention allows it to look at every other word in the entire sentence at the same time and ask, okay, which of these other words are most important for understanding this specific it right now? It's building this incredibly rich web of connections between all the words all at once.
And that was the absolute game changer. Before the transformer, AI models had to read a sentence word by word, in order, from left to right. It was slow, and they could forget what happened at the beginning of a long sentence. The transformer's attention mechanism gets this bird's eye view of the entire sentence's structure right from the get-go. And this table really shows you why that was such a huge deal. Now, don't worry about all the crazy math. Just look at that sequential operations column. For the old models, the longer the sentence, the more steps it took. It got slower and slower. But look at self-attention. It's O of 1, a constant number. That means it doesn't matter if the sentence is 10 words long or 1,000 words long. It can process it in the same amount of time. This is what makes it so incredibly fast and powerful. All right, we've taken a trip through engineering, cultural theory, and artificial intelligence. They felt like totally separate universes. But now, let's pull it all back together and see the big picture. And when you lay it all out like this, it just clicks. It's one concept, encoding, but with 3 totally different goals. The engineer encodes pixels to achieve efficiency. The theorist studies how we encode ideas to create meaning. And the AI encodes language to build a deep mathematical representation. Different inputs, different goals, same fundamental process. So, at the end of the day, here's the big takeaway. Encoding is so much more than just a tech buzzword. It's one of the most basic tools we have for taking in information and making sense of our world, whether that world is made of digital bits, cultural messages, or computational models. So we have compression, communication, and computation. The power of encoding is literally everywhere you look. And it just leaves you with this one huge question, right? What other new worlds are out there waiting for us to figure out what to encode next?